Welcome back to ECE 441A, 541A. Please remember your pre-quiz. You could do that, I guess, on your Monday off if you haven't done it already. We do have Monday off from class, and if you're looking for some review material for circuit problems, if that would help you work some of the homework problems that are due on the 10th of September, that is in the review module on B2L. And as a note, I actually added more notes at the end of class periods material on inverting a matrix symbolically or going through the various steps if you're uncomfortable with that, but there's sort of a little quick way of remembering that for a 2x2 matrix, and you'll need to know that at least for a 2x2, maybe not for a 7x7 or a 10x10, but you will want to be able to invert matrices quickly for the exams. Today what I want to do is work with a more complicated mass spring damper system, and in particular a system that has 3 masses. And if we get there, we'll try to create a state space representation. That's not even spelled right, is it? Create a state space representation for that 3-mass system. And the reason I'm putting A in quotes is we could have many different state space representations depending on how we really stack or select the state variables associated with that system's dynamics. Here's our 3-mass system that we will be working with today. Hopefully I've labeled the 3 masses, M sub 1, M sub 2, and M sub 3. Several springs to interconnect and several dash pots. We have 3 springs and 3 dash pots. And now I know you're going to ask me, where is U sub 2? Where is U sub 2? It's not there. We have 2 inputs that are labeled U sub 1 and U sub 3, mainly because the external force that's applied to mass 3, I'm just sort of connecting it with the 3rd mass and calling that U sub 3. And I do not have a U sub 2. Now that you are sketching that, I want to ask the following question. We need to assign position variables when we are modeling this system. How many position variables are needed for this particular system? And did I write well, how are you doing on copying that down? Are we about finished with copying that down? When I ask about position variables, what you can keep in mind is the following question that I want to scroll down so that I can write, but essentially it's which points can move independent of the others if all the other points were held fixed. That's how you can start to try to determine how many position variables are needed to model this set of dynamics. So my question is that I will try to write now is which points in this system can move independent of the other points if all the other points are held fixed or are clamped down. That's the question that I'm thinking you can start asking yourself when you want to try to determine how many position variables are needed in modeling this three-mass system. What's an easy position variable to think about initially? The position of mass 1. We could draw a line in the sand or put a piece of tape on, and we're neglecting the gravity in this analysis. This is on a gravityless environment, or if it's on a ice rink, if it's on a surface. Here is position 1. Let me call that Z sub 1. Well, if we just continue with that, we have Z sub 2, and we have Z sub 3. Those are some position variables that we can identify. Are there any other points in this system? If we now fixed those masses, if we pinned them down, if we lock those down, is there any other point in that diagram that can move independently? Pardon? Between K sub 2 spring and B sub 2 dashpot. Do you see that I could actually wiggle that back and forth independent of the masses being fixed? That's a fourth point that we can then identify, and I'll just go ahead and put a node there, but that could be a massless point. It could be mass 4. It's just mass 4 weighs nothing. And we now can say that this is 0.4. And when we say how many position variables are needed, now the answer should be obvious. Right? 4. So that's how many position variables we need. How many free body diagrams then are we going to need to determine the dynamics or the equations of motion for this system? We've been thinking about drawing or sketching free body diagrams when we have the masses, so you know there's at least 3 free body diagrams. THREE, 3 free, FREE, body diagrams. Do we have any more than 3? And that massless point is sort of screaming maybe at you saying, I need my own free body diagram. It's lonely. It wants some company. We now have 4 free body diagrams that we actually need to sketch. And I'm going to now, with your help, try to sketch the first one, and then we'll turn you loose to see what you can do on some others. So let's look at, by yourself, let's look at free body diagram for mass number 1. Which begins, obviously enough, with a mass. And we may want to go ahead and indicate how we have defined the variable of interest, here its position and subsequent velocity of that mass so that this now helps us when we're writing the force equations that we need to write. It's going to depend on the way that we've labeled the positions. How do you label currents in a circuit? Or voltages? You just draw them in, right? It doesn't really matter, and hopefully the analysis will work out. So don't get too hung up on, oh, I don't know if I picked the direction, positive direction of this mass properly. That's not important. The important point is writing the equations consistent with the way that you've labeled the diagram. Is that clear? So the fact that I've labeled all of these to be going positive to the right is helpful, but it's not necessary. Just like in a circuit, if you had a 4-mesh circuit, you might draw all of those mesh currents clockwise. And that sort of helps you keep your bookkeeping straight, but it's not essential, right? You just have to write your equations, your KVL equations, consistent with the way that you've labeled the circuit. Or if you've said, oh, here's V1, positive to negative. How'd you select that polarity? Well, it just kind of came out of the air, but you have to be consistent then with that labeling once you start drawing or defining your equations. The same can be said for these position labels in our diagram. I'm going to just, before I forget, write down one force that I like to keep track of, and that's the inertial force. And I keep that as a, so that's F sub I, but it's associated with mass 1. So I'm going to have crazy maybe looking notation, but this is F sub I sub M sub 1. Several subs on that F. F sub I for inertial force of mass sub 1. And now what we want to do, so now we want to determine the forces that are present when this mass M sub 1 is moved in the positive Z sub 1 direction. That's where we have to take into account the labeling. We now move this mass to the right, Z sub 1, and we say, okay, what forces now are acting because of or due to that movement of mass sub 1? So we want to identify and label those forces. And I started initially by just saying, well, if I'm moving that mass, it has some inertia, and that inertia is going to resist movement in the positive Z1 direction. It's going to be a force opposite to that movement in the Z sub 1 direction. Is that clear where F sub I sub M sub 1 came from? What else do we have for M sub 1? If I move it a little bit in the Z sub 1 direction, what other forces are acting? We have 3 different spring forces. Which direction are those spring forces oriented? What's the orientation of those spring forces if we move M sub 1 in the positive Z sub 1 direction? They're going to all be pointing to the left, are they not? So let's now label those, and I'm going to have multiple free body diagrams with similar or with the same springs. So I'm going to make these forces start with a left subscript, labeling with a 1. meaning I'm going to say I have a force due to spring 1, K sub 1, but that's in free body diagram number 1. So that if I now have another F sub K sub 1 in another free body diagram, I'm going to label it on the left with where that free body diagram, or consistent with that free body diagram. And we have the force due to spring 2 in free body diagram number 1. We have this force due to spring 3 in free body diagram number 1. We had an externally applied force, U sub 1, and we can't change its direction. It's oriented in the towards the right as positive U sub 1. And do we have any other forces that we need to worry about? We have the dash pot. And to find the dash pot force, what I like to do when you're first learning these is just treat it like a spring and say, okay, what variables are involved in the force due to that dash pot? But the dash pot's force, this dash pot constant, is going to be B1 times the velocity of the two ends of that dash pot. The difference between those two ends. Just like the spring are dependent on the positions, the dash pot is dependent on the velocities. In this case, I have Z sub 1, its velocity, Z1 prime, if it's going to the right, then multiplying that by B1 will produce what kind of a force? If I move to the right, mass 1, in the positive Z1 direction, what direction is the force due to that dash pot going to be directed? To the left. Does everybody feel comfortable with that? So now I have an F sub B sub 1 in free body diagram number 1. Though that's now my complete free body diagram for mass number 1. I have 1, 2, 3, 4, 5, 6 forces in one free body diagram. What I now need to do is, well, you can do it however you want in whatever order. I'm going to just say now we want to actually define the forces. You could sum these forces algebraically, or say the sum of the forces equals 0, just like KCL says the sum of the currents are 0, or N's equal ounce in terms of currents into or out of a node. Here we have forces to the right equal forces to the left, is another way of saying that. And then we could say, okay, what are those forces? Let me just start writing the force expressions, and then we'll write the equilibrium equation, and then we'll plug in the force expressions to that. That's the order that I'm going to do it. So for now, what I want to do is define the forces in terms of the coefficients, and the coefficients now are K sub I, B sub I, M sub I, depending on which free body diagram we're in, and the positions velocity and acceleration, since we have ma in the inertial force. What is F? How do I say this? F in front 1 sub K1? I don't know. F1 sub K1, how's that? F1 sub K1, what is its expression in terms of coefficients, positions, velocities, and accelerations? That's just K sub 1 times Z1, because its leftmost end is stationary. So whatever Z1 moves in the positive direction, that's going to produce a positive force the way that we've drawn it. Is that clear? Yes. Again, I don't know why. The question was, why are we not considering a gamma U sub 1 anymore? That gamma was just it's actually a conversion factor in the lab. And so I tried to put it on our generic mass spring damper system because it will be a part of your dynamic equations in the lab. Here, that I'm not even worrying about having a conversion factor or any other. I'm just going to say U1 is the force. I'm not going to weight that by some gamma. But you could if you had conversion factors that were necessary in your system. Here I'm saying that we have enough coefficients floating around. Let's not introduce another one. Is that okay? So U sub 1, you could put a scaling factor in front of it. Here I'm not going to. I'm just going to say U1 is a force. But if that was being produced electrically, you obviously would have a conversion factor to say convert that voltage or current into a force. And so you would have a scaling factor associated with U sub 1. Where were we? F1 sub K1 we said is K1 Z1. If Z1 moves positive in the positive direction that we've indicated, that will produce a positive F1 sub K1 in the direction that we've labeled it. That's what we want to make sure is consistent. What about F1 sub B1? What's going to produce a force in the left, positive force to the left, when we have a velocity of mass 1 to the right? Just B1, the dash pot coefficient, times Z1 prime. That's our dash pot force relationship. It's the coefficient B1 times the velocity, or difference of velocities of its endpoints. Here we just have one end of that dash pot that's free to move, and that's the Z1 end. What's F sub I sub M sub 1? That's Newton, isn't it? That's mass times acceleration. That's now M sub 1, Z sub 1 double prime. What about F sub 1 sub K sub 2? I'll do the hard part. It's K sub 2 times something. Now what is going to produce a positive force to the left relative to this overall block diagram? Now we need to consider both ends of that spring. And how do we define the force? K2 times something, such that its two ends, when they produce a positive result, give us a positive force to the left. And what could you do if you're a little bit unclear? You could say, well, let me just start with what I know. Suppose Z4 was fixed, didn't move. Then you know how to write the force equation. It would be K sub 2 Z sub 1. Yes? Okay, well, let's put that in. We have K sub 2 times Z sub 1. Now we have to figure out, how does Z sub 4 figure into this? Do we say plus Z sub 4? Minus Z sub 4? Times Z sub 4? Why does he want Z sub 4 in there? Do you see? So now everybody have a pen, an old mechanical style ink pen that they can tear apart and pull the spring out of? I'm just trying to get it. No, you don't have to, but I'm doing this virtually. We don't have virtual headsets, but that kind of helps me think through what's going on. You have two ends of that spring, and now you're trying to figure out, how am I going to produce a positive force going to the left when I have two ends of that spring labeled Z sub 1 and Z sub 4? What if I moved Z sub 1 the same distance as Z sub 4 is moved? How much force is that going to produce? If that spring presently is in an equilibrium state, the way I've drawn this diagram, and now I move Z1 the same distance as Z4, what have you done to the contraction or expansion of that spring? Nothing, have you? So should it produce a force? How do we get Z1 and Z4, compare those to produce 0? If they're equal in value. Z1 minus Z4. Right? We can't do Z1 plus Z4, because then we would have twice the force when we really know there shouldn't be a force there. I'm trying to get us to think through where this expression is coming from, but I'm going to now write that this force is legit. The force F1 sub K sub 2 produced by spring 2 is K2 times the difference Z1 minus Z sub 4. Now if I had sketched Z sub 4 in the other direction, then it would be a plus Z sub 4. Is that clear? So drawing all of your positions moving in the same direction allows you to sort of have this consistent Z1 minus Z4. Suppose you're still confused on this labeling. Go back and say, what if I fixed Z1 and now I moved Z4 in the positive direction? What force is going to be applied to mass 1? It's going to be a force going to the right, which is the negative of how we had sketched it, right? So we have a negative F1 due to K2. Is everybody seeing that? The signs take care of themselves is what I'm trying to say. Just like when you write KVL equations with clockwise currents. You maybe have I1 minus I2 in a shared resistor, for example. Comfortable with that? What about F1, the last one, F1 sub K sub 3? And you have to go back to your original diagram, see how you have labeled it. Whoops, it's not labeled, is it? So Z1, Z3, Z4, and Z2. Now you're playing with Z1 and Z3. What's the equation going to be? To produce a positive force going to the left in this free body diagram. Was my explanation that poor before? Okay, we have K sub 3. That should be pretty clean. And now we have Z1 minus Z sub 3. Now we can use all of those expressions to write our equation associated with free body diagram number 1. We want to say the sum of the forces equals 0, and this is now an algebraic sum, so if we have some forces going to the right and some going to the left, we introduce a negative sign, or we say forces right equal forces left, however you want to think of it, but the sum of the forces equals 0. The algebraic sum of our forces equals 0. And if we look back at this diagram, we have 4 forces going to the left and 1 going to the right. So we can label or write these however we want, but we could say F1 K1 plus F1 B1 plus F1 K2 plus F1 K sub 3 is equal to U1. Whoops. How could I forget the inertial? That's why I said I wanted to write it down first, right? Maybe because I dashed it. But we have that inertial force in this case. So we have 5 forces going to the left and 1 going to the right. To write down the underlying dynamic equation now, consistent with the way we've labeled the positions, let me shuffle these a little bit. Let me write F sub I sub M sub 1 first so that I have my higher derivatives to the left side of my equation. I now have M sub 1, Z sub 1 double prime. And these are arguments of time. I'm going to not include those for space purposes. We then have plus B1 Z1 prime. So I've accounted for that one. I've accounted for that one. Plus K1 Z1. There's that one. Plus K sub 2. Where was that one? That one was Z1 and Z4. Z1 minus Z4 plus K sub 3, Z1 minus Z sub 3 equaling U1. One, two, three, four, 5 were going to the left and 1 was going to the right. That's now one piece of this set of dynamic equations that we need to write for this 3-mass system. And it should make you feel sort of comfortable because we were writing the free body diagram for mass 1, and that's mass times acceleration of that mass, and that's Z1 double prime. M1 Z1 double prime figures into this set of equations. Let's see how well I presented that by having you sketch the free body diagram for mass number 2. And if you're brave, you can pull out the whiteboards if that's easier. So I want you to sketch free body diagram number 2, or for mass number 2, I should say. It's going to take you longer to get the equipment on the table than to write the free body diagram. Are we finished? You have to refer back, yes. Question?
I'm so confused on the difference between these, because the way I set it up is that I kind of just assume this is kind of an absolute value, and this negative takes care of the direction. So it's Z4 minus Z1.
It's however you want to do it. So if you've derived these other ways, that's okay. But it needs to be consistent. You need to end up with the resulting differential equation that I ended up with.
Yeah, it's a bit different, that's right.
And it shouldn't be any different.
I get Z4 minus Z1, where Z3 minus Z1, whereas you get.
So we may want to talk after class and see how we can rectify that. Does everybody have free body diagram for mass number 2? Is it as busy or detailed as mass number 1? No. Did everyone forget the one that I never want to forget? This is, how am I labeling this? Let me say this is F sub I m sub 2. There's your inertial force. If you push this mass to the right, it's going to resist that. It's going to have some inertia, and it's going to oppose. It's going to move to the left. What other forces are in your free body diagram? Is it plural? Do you have more than one force besides the inertial force? Isn't there just one due to the dash pot? And if our labeling is the same, it's F2, was it B sub 2 to the left? And what are our equations? Now we have F sub I sub m sub 2 is m sub 2 z sub 2 double prime. What's F2 b sub 2? Did I remember my primes in the z's? I guess I just had one. Yep, okay. Are we okay with that? And now we simply write the equilibrium equation, the sum of the forces, to produce. These are both in the same direction. And so those have to sum to equal 0. Or we now have m sub 2 z sub 2 double prime plus b sub 2 z sub 2 prime minus z sub 4 prime is equal to 0. We comfortable with that? Let's talk our way through free body diagram number 3, or for mass number 3. And what else did I have in that particular mass 3? I have an externally applied force going to the left, and I have to make sure that it's going to the left. And I have a spring on the left. Which direction is positive force going to be associated with spring K sub 3? To the left if I'm moving positive z sub 3, and b sub 3 is going to give me a dash pot force to the left. So I now have, I was trying to avoid having to scroll, and it reset. So now I have u sub 3, f sub 3 of b sub 3, and f sub 3 of b, k sub 2. Is that everything for mass 3? Go back. Pardon? I was just checking to make sure you guys were even paying attention. K sub 3. Thank you. Any other errors on the board? No? Sum of forces equals 0. All of those are going in the same direction. Now the applied force is going in the same direction as the others. We now have F sub I sub m sub 3 plus F3 of B sub 3 plus F3 K sub 3 plus U sub 3 equals 0. And I should be able to now write all of these down. My inertial force is m sub 3 z sub 3 double prime. What's F3 sub B sub 3? Now it helps to go back and look and see what we had. If I now move in the positive z sub 3 direction relative to b sub 3, that dash pot, what needs to multiply b sub 3, expression-wise? One of the ends of that dash pot is fixed, is it not? So we really just have one variable. And if we move in the z sub 3's positive direction, the way that we created the positive force associated with dash pot 3 to the left gives us b sub 3 z sub 3 prime. What about k sub 3? How do I obtain a positive spring force to the left associated with k sub 3 relative to z3 and z1? I need z3 minus z1. Are we okay for that equation? Now let's look at the last free body diagram, which is for our massless point. Massless point number 4. Now we can just draw a point on our page. And we have it labeled as z sub 4 positive to the right. If I now displace that massless point positively to the right, what forces will be experienced by that point? If I move to the right, z sub 4, if I move that point labeled z sub 4 to the right, what forces do I need to draw that will oppose that movement? How many forces do I have? 2, one due to the dash pot, b sub 2, another one due to the spring, k sub 2. They're both opposing that movement to the right, and so they're going to the left. The free body diagram now for massless point number 4 is a force F4 due to b sub 2 and a force in the fourth free body diagram due to k sub 2. If I sum the forces, I now have F sub 4 B sub 2 plus F sub 4 K sub 2 equaling 0. and what are those, what make up the expressions for those forces. I go back to my original diagram and I say, what's going to give me a positive force to the left associated with spring K sub 2? Which one? Let's do dash pop B sub 2. What's going to give me a positive force to the left for dash pop B sub 2 relative to this diagram? And what do I multiply these dash pot coefficients by? Positions, velocities, accelerations. Velocities. So I know that I have to have velocities, single primes. Pull out your spring from your pen again and think about the dash pot, and which way do we have? What's in the parentheses? There. If Z4's velocity is bigger, more positive than Z2's velocity, won't I get a positive force going to the left? I now need Z sub 4 prime minus Z sub 2 prime. Now I have Z sub 4 and Z sub 1 on either side of spring K sub 2. And there is now the expression I need for F4 sub K sub 2. Or I now have my equation will be B sub 2 Z sub 4 prime minus Z sub 2 prime plus K sub 2 Z sub 4 minus Z sub 1 equaling 0. Now that I have all of these differential equations that are coupled, I have Z1s, Z2s, Z3s, Z4s sprinkled around with their derivatives once and twice. In all of these equations, there's coupled equations. What's my system matrix dimensionally? What's my A matrix if I put this into a state space representation? Or another way to approach that is to ask, how many state variables do I need to describe this system in a state space representation? So how tall is my system vector? Or somebody might say, what's the system order? What's the order of this dynamical system? If you looked at the very first equation for free body diagram for mass number 1, what's the highest power derivative of Z1? It's a second derivative. So there's two states. I need a position and a velocity, and if I differentiate the velocity one time, I'll get the acceleration. So there gives me 2. What about mass 2? 2 more, right? Mass 3, 2 more. I have one more equation that's still on the screen, and what's the highest powered derivative of Z sub 4? 1. So do you see my fingers? Those of you at home, can you see my fingers? Tell me if you do. Send me an email if you can see my fingers if you're at home. But hopefully you've been counting up, and now we know that we have a system order that's 7th order. We have 2, we have position and velocity for the masses, So we're looking what? At the highest powered derivative of each of these equations, or each of our variables. That's what we need to add up to get our system order. Our system order is 7, and we can find that by adding up the highest powered derivative of each variable. The Z1, 2. The Z2, 2. The Z3, 2. The Z4, 1. 7th order when you add all of those up. We'll pick up at that point on Friday.